And then we move on to a second speaker after the break. That's Fabian Bruning. Fabian is a co-founder of FononTech. Let me give you this one. And FononTech reached the Dutch headlines as they can reduce the ecological impact of microelectronics manufacturing by a factor of 1,000, I read. So Fabian, please share more about that.
Yes, as introduced, my name is Fabian Bruning, a co-founder at FononTech. And FononTech is a company located in the Brainport region in Eindhoven. We're a spin-off of HolCenter, and we are working on a new printing technology called impulse printing. So as you saw in many great talks today, consumer electronics are getting smaller and more powerful. And that also means that all the components have to become smaller and more powerful. So there is a huge drive in the front-end semiconductor historically to create smaller and smaller chips. So semiconductor companies like Intel, TSMC are inventing new processes to make the transistors on the chip smaller. ASML is doing a lot in lithography to make that possible. Then you have chips that are packaged, so they get packaged in multiple packages or together. That's called the back-end industry. And then also you saw great innovations today from HolCenter and from Traxon on circuit board manufacturing, which are also getting smaller and more innovative. But the front-end innovation is stagnating. So ASML has said that by 2030, Moore's law is ending. There is no way to get thinner and thinner traces on a chip. So a lot of the innovation is shifting to the back end. So in the back end, there's currently advanced packaging innovations, introducing chiplets, but also heterogeneous integration, where you have multiple different chip processes together in one package. And there are some challenges to go from conventional packaging, where you can see there's typically one chip inside of a package, it's wire bonded, to multi-3D advanced packaging, where also chips are together on multiple layers, but they are also integrated in a package more efficiently. So what are the requirements for the scalability of 3D packages? You need micrometer features, so features that are typically 2 to 30 micrometers. You need complex 3D interconnects to be able to connect chips together stacked or besides each other. And you need to do this at high volume. So the chip industry is, of course, a high volume industry, and there are not many solutions that combine these three together. So for example, when you're wire bonding chips, that is currently very fast. You make 100,000 wire connections in an hour. But when you go to smaller and smaller chips, such as the micro-LEDs that Gary showed in the beginning of today, you need millions of connections per hour. But with a single nozzle, or dispensing, or wire bonding, that's not possible. The technology is too slow, and thus also too expensive. Mask-based technologies such as screen and stencil printing, they're extremely fast, but they are limited when the substrate is not perfectly flat, or when you need to compensate for substrate warpage, or maybe you even have a mix of chips on your substrate. So first you want to do, for example, one type of chip and then the other type, then you cannot stencil print anymore because the first chip was already placed. So in summary, there's no printed solution for high volume manufacturing of 3D interconnects on these kind of panels which are warped, bent, and otherwise out of shape. So in 2019, the founders of FononTech invented impulse printing at HolCenter. And impulse printing is a new printing technology where we use rapid thermal transfer. And in this case, it's based on electrical heating. So we have an impulse printing plate, and this plate is made on a 200mm wafer process. And there are thin film heaters on the plate. And on top of those heaters are grooves. So we fill the grooves with a material, and that can be any material that evaporates below roughly 700 degrees Celsius. We first fill the plate, and then we extremely rapidly heat it, and then we go back to room temperature, all in much less than 1 millisecond. You can see the process in the video here. So this is a schematic representation of where the grooves are filled. Then the substrate comes in, and then immediately the entire pattern is transferred. So you can transfer not only dots and lines, but also full text, as you see here. And you don't have to do it one by one, so it all comes at once. So this enables micrometer-sized features, because we make the plate using lithography. So you can go all the way down to 1 to 2 micrometers in size. You can print complex 3D interconnects because this technology enables shearless printing. So you can also, as you see in the schematic, you can print over a chip, but you can also print inside deep cavities or even around the substrate, which is what I will show later. And you can do this at high volume, so the entire plate can be printed at once. So we can print millions of interconnects in an hour, depending on the size of the interconnect. So the size options of the technology, the basic process is using an engraved plate, so the grooves are actually inside of the plate. And this has a size limitation because of the depth of the groove, so we can do between 1 and 10 micrometers deep and between 2 and 80 micrometers in size. We also have a technology where you have the flat impulse printing plate, which is basically a 200 millimeter wafer with only the heating elements. And then you can use a 2D printing technology like screen or stencil printing. And we can make that non-contact and also semi-digital. So we can compensate for substrate warpage, but also we can print at quite large print gaps. So you can suddenly use this 2D technology, which is very fast and cheap, in applications that were not possible before. As an example, here you can see the size range of impulse printing also compared to other printing technologies. So you have very low, high resolution technologies on the left and lower resolution on the right. And you can see this pattern here contains 15 and 20 micrometer lines. And this entire pattern, including the neighbors that are not in the picture and the text, is printed all at once. So you can really make extremely high production rates possible. Shearless printing, I mentioned it before, but because we heat uniformly in the entire heating structure, we can print without shear forces during the transfer process. So we can print almost any viscosity. We've printed water, which is too low for inkjet, for example, but we've also printed viscosities that are almost like paste, like peanut butter type of materials. And the big advantage is that with sometimes even with the same settings, you can print, for example, copper inks, silver inks, which are commonly used, as we saw earlier today. You can print dielectric inks, but also carbon inks, plating precursors. You can print solder pastes. Here you can see also in this image how big the Dopplers are. So we've printed type 7 solder paste, but also type 8 and 9, and also larger than that. You can print conductive adhesives, which don't even include a solvent, but there you evaporate a tiny bit of the polymer material. You can print the die-attached materials, and you can also print these at a gap, so for on panel level packages, for example. And we can also print low viscous materials, such as underfills, which can even flow after printing. So you can have fast underfill printing on almost any substrate. So also, especially when you have densely stacked chips, you can print with underfill contactlessly, so you don't have to use needle dispensing. And very high viscosities enable things like wet-on-wet multi-layer printing. So in this image, you see 20 layers that were printed with a copprint material. And this is a beta material from copprint, which is more high viscous than their normal materials. And on the right, you see pillars which are 750 micrometers high. They are 250 micrometers wide, and these are 20 layers on top of each other. So the basic process is that you stencil print on the flat heater, you transfer it, and then you refill the plate and you transfer it again. And this can all happen extremely quickly. So in an R&D setting, on our alpha tool, that looks like this. So in the alpha tool, we have a robot arm to move the substrate. And this is because we can print in this 3D way. With the robot arm, you can hold the substrate under any angle. For the high accuracy version, we are now working on a more accurate system using granite air bearing stages. And on this tool, you have basically all the basic components that you need for impulse printing. So you have substrate handling, you have plate filling, and you have a camera. So that looks like this. So now the first layer is printed. Then a custom filling system comes in and refills the plate with a stencil, in this case. And then the second layer is printed. And here we are using only one heater element that's 5 by 5 millimeters. So you see two heating elements in the image. Only one is printed. So now the stencil is coming in. And then you see a very tiny amount of material being transferred. And these are actually the pillar structures that you saw in the previous image. But without a microscope, it's quite difficult to see. And in the back, you can see all the materials we've printed. I promise next time we'll clean that before we make the video. And yeah, that's basically the printing speed. On our new beta tool, this will be about 400 times faster because we have a full 200 millimeter wafer with 256 heating elements. High viscosities also enable the ink to follow a topology. So on the left you can see the types of topologies. So 2D smooth is always very common, so printing on glass and printing on smooth foil is a very high TOL technology already. 2D rough becomes a bit more difficult. And then you have 3D simple, where you can use technologies such as aerosol jet, but also dispensing, to follow the contour. But 3D complex, and that's more new. So in this case, we printed a line of copper ink, and this line is falling down from the top. It's coming down, it hits the chip first, and then it follows around the contour of the chip. And you can see here something that looks almost like a wire bond, so a free-floating copper line. In this case, this corner behavior is also tunable, so we can use structural thermal buffer layer to shape the way that the ink flies. And in that way you can tune the behavior in this blind corner. Another possibility is to print over a gap. So when the ink is very thick, when it falls down, it will just stay. So this is liquid ink, and it's suspended over a gap of 2 millimeters. In this case, between two glass slides. But of course, this could also be on a package or on a lead frame. We show it here with copper ink, but in practice, you would first print the dielectric ink as a bridge. Then you would print the copper ink, and then you would usually also insulate it. And I mentioned it before, but printing a wraparound, that is when you print on the edge in this case. The line hits the edge, and then it wraps around the two corners. So you can do that in two ways. You can do it from the bottom, but you can also do it from the front. And in this case, it's made from the front, and it wraps one time on the top and one time on the bottom. So now with many lines at once, on the beta tool it's 400 lines per heater, you can make a front-to-back interconnect. So this is a silver ink on a glass that is a similar thickness to what is in a phone. So when you make this interconnect in this way, you can make a phone thinner, you can make the front-to-back interconnect faster, and you avoid using true glass or true silicon vias, depending on the substrate you're printing on. With this interconnect, you can also enable screens like this to be made from multiple panels, because the interconnect is thinner than the pixel pitch. So the space between two pixels is larger than the size of the interconnect. So if you want to connect two televisions together, now you will always see a gap. But with this technology, you can make an interconnect that is invisible. Here we show this also in an animation. So for micro LED, there are two main applications. That's making the top and bottom interconnect. So that's printing the bumps before the die is placed. But also when you flip chip an LED, a lot of wafer area is actually used for the front-to-back interconnect, because when you flip chip, part of your LED die contains interconnects. With this technology, you can also place the LED, make a bottom connection, and then you can afterwards insulate and print the top connection. So you can make a 3D interconnect, and then you can do that with millions per hour. And the second application, as I showed before, is the wraparound electrodes. So you can connect two of these display tiles together, and then also make the connection between the LEDs and the display driver. In the animation, that looks like this. So from the top, there is a line falling down, and then it flips around the edge, and then it makes a functional connection. And in real life, that looks like this. So we put a timer on it because otherwise you will miss it. It's extremely fast. So on the right image, you see a glass slide that's 1 millimeter thick. And 5 lines will shoot from the bottom. They will hit the glass slide and they will wrap around. And you will see that 4 lines come earlier and the 5th comes later. And that's to show the digitalization possibilities of the technology. So in this video, each of the lines are on an individual heater. So as you see, 4 come almost instantaneously and the 5th comes later. And imagine now, if you make this with a different print, with a single nozzle printing technology, you would have to trace each of these lines. one by one. Yeah, and then if you have to do 10,000 per phone, it will take quite some time. So there are companies that show this as feasibilities, which is very good. And it's also very good because single nozzle technologies can be used in combination with impulse printing to repair. So if you miss 1 out of 10,000, you can repair it and make a high yield production. So at this moment, these lines are 200 microns. We've shown them as 50 microns, and next year we also want to show them 10 micrometers and smaller, which is the display pitch that is used on current phones. This all comes together in this animation. So in this animation, you see a lead frame placed on a printed circuit board. On the bottom is solder paste. And normally you would, of course, first package the chip and then place it on the PCB, but here it's artistic license. And then on top of the lead frame is die attach and a silicon die. And when we print the interconnects, you first see that the dielectric comes down. It follows the corner, as you saw in the images previously. And then you can print conductive inks. And then it depends a little bit on the material system if you would need to cure this in between. Some material systems you can print directly on the dielectric, but some material systems you have to cure in between. But that you can do quickly in the oven or with flash curing. A practical example of this coming all together is chip-to-board wraparound. So here we have a printed circuit board that's 1.5 millimeters thick. And you can see that on the image on the left. And there is gold contacts on one side. And then we bond a silicon chip directly to the printed circuit board. And in the current product, there is a wire bond running from the silicon to the printed circuit board, which increases greatly the area that's required to make this interconnection. And for this application, that's undesired, because this application is meant for in your mouth. The size limit is at the edge. You can imagine smaller is better in this case. So as a demonstration, together with a customer who allowed us graciously to show this, is that we can print 80 wraparounds, and we do that in 5 shots, so 5 times print on the alpha tool. You saw previously how quick it is, so roughly the length of the demo video it takes to print this. And then you make a silver interconnect on top of an underfill. And the underfill here is meant to insulate the edge of the silicon chip, because that is still conductive. So with impulse printing, we can print on the silicon chip to place the underfill. Also, it matches the CTE of the PCB, so it is a kind of a CTE bridge between the silicon and the PCB. And also, you can see a little bit in the animation, in the illustration, that there might be a gap depending on how well the silicon chip is placed. Then we print the wraparounds with a conductive paste, and then we overmold it. And you can see in the zoomed-in picture the quality of the wraparound. Also, you can see on the image that the PCB is not perfectly flat, so the gold contacts are actually extended a little bit. But the silver, in this case, just follows the contours. You don't need to tune really anything, and you can print this even at pretty high standoff distance. So if you have any product variation where your silicon chip is not perfectly placed, of course, within reason, you can still print it. Also, our customer thermal cycle tested this, so we have now done initial thermal cycle testing of 50 cycles at -10 to +60. So that's not the automotive spec yet, but it's close to consumer grade. And we see no deterioration after 50 cycles. Actually, we see some lines even improve in connectivity. And the resistance is about 0.3 ohms. And these samples will now go for extended reliability testing, also for 85 degrees Celsius and 85% humidity. The product of FononTech is an impulse printer or a print head. So we deliver the technology basically as a printer for end customers, but we are also looking for, of course, for integrators who would like to integrate impulse printing, for example, directly into a die bonder or directly into a printing system where you screen print and combine it with impulse printing for advanced packaging, but also for printed circuit board applications. We also make the plate. At the moment, we do that at the high-tech campus, but we also plan to open our own wafer fab in the Eindhoven region, so we can supply in high volume these custom impulse printing plates. Then customer comes with a 2D design, and with any material. So we don't make our own materials, and we have an open material system because we can print almost any material. And then we can make impulse printing possible for the customer. Sustainability was mentioned by Jorik previously. So the way we calculated it is that we make the plates with lithography, but this lithographically made impulse printing plate can then be used to impulse print, which has very low emissions. So for every lithography step, we can print at least 1,000 times with the same plate. So you can see it as spreading out the exhaust and the emissions that were generated by making this plate with lithography and dividing it by a factor of 1,000. And then we also calculated, of course, the impact of the additive process, but that's far below. I would have to add a lot more zeros here to be able to show that in this image. So the message basically is additive impact is quite low. And this is a calculation compared to back-end lithography. Of course, there are also other technologies where you can calculate. So at the moment, you saw the Alpha tool in the video. So this has two 5x5 millimeter area print zones. It can handle substrates up to 100 by 100 millimeters. It's located at Hol Center, and it's available now for R&D projects. And the Beta tool, the system, we expect to have the first print in December and to have the first delivery in Q2 2024, which has 128 by 128 millimeter print area, and it can handle substrates up to 300 by 300 millimeter for high resolution and lower resolution 300 by 400 millimeters. So it can has also multiple vacuum zones, so it can directly handle 300 millimeter and 200 millimeter wafers, as well as rectangular substrates. And the way the Beta tool plate layout is that it has 256 individual print zones, as I mentioned earlier, but here you see the layout. So each of these zones of 7.5 by 7.5 millimeters can be triggered at once. So you can do multi-layer printing, you can do the whole, about 10 to 20 of the pillar structures that you saw earlier all at once. And we have closed loop heat flux control. So we have very reliable and very precise heat flux repeatability and fluence repeatability. And the print time of all of these zones is less than 100 milliseconds. But in practice, we see that most customers would like to do either local alignment or moving on layer, and then the print time is expected to be about 10 seconds per plate. Then you can also experience impulse printing live because we use electrical heating. It's in essence, it's quite a simple system. So we made a low power version of impulse printing, which works on a battery, which I actually have here in the box, which is a little bit heavy, but what you see here is a complete impulse printing system. So it has 3 zones with silicon wafers. And you can print a wraparound directly at the table in the demo room, where I will be later today and also during the reception. So if you want to print a wraparound yourself, feel free to come up and press the green button. Thank you.
Well, thank you, Fabian. Very interesting to listen to the innovation technology that you developed, and like also looking into application fields. What are like the goals of your company for the upcoming years?
So our first goal is to launch the Beta tool. So this is really meant so customers can do their own R&D. Because in the chip packaging and display industry, we see that customers, of course, need to design their product for impulse printing. So then you can use the impulse printing R&D tool to first design the product. And for existing applications, it's typically a bit easier where a customer already has a material and a process, but they need, for example, better reliability or accuracy. And then the next step in 2025, 2026 is to launch the production tool. So we build a wafer fab to deliver the plates. And we built the first production tool and also the production printhead, which is available for OEM integration.
That's what you mentioned. You want to create that somewhere in the Eindhoven region.
Yes, indeed. Yeah. Because we need a very small fab, and then we can, the productivity is quite high. Yeah. So you can, with 50,000 plates, you can service, I think, twice the yearly phone production. Yeah.
Very cool. You have a demo tool. So if you want to take a look, please go to the demonstration table of Fabian afterwards during the network drinks. So Fabian, thank you for your presentation.
Thank you.